Okay, hopefully you're feeling good about the Moody diagram and looking up the values. We're going to put that to use now. So here's the next problem in your package. Benzene at 50 degrees Celsius, specific gravity 0.86, is delivered to point B with a pressure of 550. Point A and point B are connected by 240 meters of plastic pipe that has inside diameter of 50 millimeters. If the volume flow rate is 110 liters per minute, calculate the required pressure at the outlet of the pump. Minor losses are negligible. Now, be careful. Just because it says minor losses are negligible, that does not mean that HL is 0. We still have to calculate the friction component. So please be careful on that if you get that sort of a question. Okay, before we begin, or as we begin, something I like to do, you don't have to do it this way if you don't want, but I usually like to look up the properties of the pipe and the fluid right away just to get it done, and then I can just proceed onward with the problem. So you can see what I did is for plastic pipe, well, it just said plastic pipe with a 50 millimeter inside diameter. So we actually didn't have to go to our appendices to look up any values. It was given as D, and then I just did the calculation to get my cross-sectional area. And epsilon, if you go to your chart, and I'll use this one right here, you can see that for glass and plastic, the relative roughness, it says smooth. Not a number, but smooth. Okay, well, I'll explain that now in a minute, but we'll make a note here that epsilon says that it is smooth. Now next, for benzene at 50 degrees Celsius, we were given a specific gravity of 0.86, and so therefore we can get our rho as 860 and our gamma as 8437 through calculations that we've done before. And to get the dynamic viscosity, we're going to use our appendix D. So go to our package like so, go to appendix D, which is a graph like so. Okay, so we have benzene at 50 degrees Celsius. So so we'll go right here. There's our 50 degrees Celsius on the bottom, and we've got to read up to benzene, and benzene, the line is right here, so it's just a little bit above that line right there. So we read across like so and get our value right there. So it's a little bit above 4 times 10 to the minus 4. So I actually took 4.2 times 10 to the minus 4 Pascal seconds as my value for dynamic viscosity. Okay, so we've got that stuff out of the way. So it's usually good to do that, and we can just start right in on what's going on. Well, let's look at our energy equation. So we've got point A and point B. We're going to take, obviously, point A is the what we're interested in at the outlet of the pump. Point B we're going to take because we've got information, we've got height. We don't have velocity, but we can get it. And let's see. Now, also give consideration to our shortcuts. So we think of points open to atmosphere is not applicable here. Large reservoir, not applicable here. Points at the same height, not really applicable. And points with the same diameter. Well, A and B, as it turns out, have the same diameter, so that'll work out to our advantage. So, since we've got the same diameter for both points, we can say that D1 is equal to D2, therefore V1 is equal to V2, or I should say VA is equal to VB. So they can cancel out like so. ZA, I'll choose my datum. As you can see, I've got that chosen right there, so my ZA is gone. And now, this might seem a little controversial to you. I'm going to get rid of HA and HR. Okay, HR you might buy easily because we say, okay, there's no devices removing energy, so HR. But HA, what about the pump? Well, don't forget, the pump is not between point A and point B. So, between point A and B, there's no devices adding energy. So, over here we could have 3 pumps, some 5 turbines, and 2 motors. Doesn't matter. Between A and B, no devices add or remove energy, so they're both gone. HL, even though minor losses are negligible, we still have to get the friction component. And then PB we've got, and ZB we've got. Okay, so let's see. So the big thing now is we've got this, we're looking for this. We're going to need to get HL. So this is our first time really getting HL. So first step is to get Reynolds number. And Reynolds number is rho VD over mu. So we've got our rho, we've got our D, we've got our mu. We only need our velocity. So we need V. So I'm just going to say V is Q over A. Our Q is 110 liters per minute, and that's times 1 minute per 60 seconds times 1 cubic meter over 1,000 liters. And then our area I had already calculated as 1.963 times 10 to the minus 3. That gave a velocity of 0.93 meters per second. So now I can get my Reynolds number is going to be equal to 860 and 0.93. I'm skipping my units in the interest of keeping this short. 0.05, and our mu is 4.2 times 10 to the minus 4. Oops, 4.2 times 10 to the minus 4, which actually gives us a value of 9.5 times 10 to the 4, which is greater than 4,000. So that is turbulent. Okay, so we know that we've got to use our Darcy's equation. So now we need d over epsilon, Darcy-Weisbach equation to get that. So we need a d over epsilon. Our d over epsilon is what we said, 0.05 over smooth. Well, what do I do with that? Well, what that means is use the smooth pipes line. And let's see. So on our sheet, note on the bottom here, there's our smooth pipeline right at the bottom. So what that really means is once we get to 5,000, 10,000, 20,000, we're going to get up to very large numbers, and really once it gets so high, they get to a sort of a maximum value, which is where the smooth pipeline is. So that's what we've got to do, is use our Reynolds number is equal to 9.5 times 10 to the 4 and our smooth pipeline. So 9.5 times 10 to the 4, let's see if I can get this all in here. Here's 10 to the 4, 10 to the 5, 9 times 10 to the 4. There's 9.5 times 10 to the 4 right there. I go all the way up to the smooth pipeline, and I'm just a hair below that line, probably. And then I'm going to, sorry, this might be a bit hard to follow, but if I get this nice and flat, you can see we can read across to right there. And I'm going to call that pretty much on the line. That's 0.018. Hopefully there's no argument over that. If you wanted to call it 0.0179 or 78, that's no problem. F is equal to 0.018. Alright, now we go to our Darcy's equation. Remember, for turbulent flow, we can only use the Darcy's equation. FL over D V squared over 2G, 0.018. No units, by the way, if you were wondering. Dimensionless. L we were given as 240 meters. Our D, of course, was 50 millimeters, 0.05 meters. And our V, 0.93, all squared, over 2G. And an HL there should come out to be 3.83, and the units are meters. So let's go back to our Darcy's equation, Darcy-Weisbach, our energy equation. I'm just going to put my asterisk up here and just bring this back down here. And now we've got PA, let's just rearrange it. PA is equal to gamma outside of PB over gamma plus ZB plus HL. That is a gamma, that's not crossed out. So that will be 8437 outside of PB, 550 times 10 to the 3 over 8437 plus ZB, which was given as 21 meters, 21, plus 3.83 meters, and we should get PA is equal to 759 times 10 to the 3 pascals. How's that? Hopefully that works for you.